Hello and welcome to Lecture 6 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to derive a major result of statistical physics, the partition function. So in Lecture 4, we looked at this example where we made a list of states of the total system, assuming that system A had 2 coins, system B had 3 coins, and that the total energy was U0 equal 2. And we also learned that the multiplicity of the total system was given by the product of the multiplicity of system A and the multiplicity of system B, and that the multiplicity of system A must be evaluated at the energy of system A, and the multiplicity of system B must be evaluated at the complementary energy. So this term is the number of states of system A having energy UA, and this term is the number of states of system B having the complementary energy. In other words, it is the number of states of system B that can combine with states of system A having energy equal UA. So if we ask how many times does the state HH appear in our list, the answer is it appears 3 times, and it appeared 3 times because the multiplicity evaluated at the complementary energy, in this case the energy of the state HH is 0, so this term is 0, so the complementary energy is 2, so GB evaluated at the energy 2 is equal to 3. There are 3 states with the complementary energy. So this state can combine with these 3 states to form a state of the total system. And if we ask how many times the state HT appears, the answer is also 3, but now because the multiplicity evaluated at the complementary energy, now this energy here is 1, so we have 2 minus 1, the complementary energy then is 1, so GB, the multiplicity of system B evaluated at 1 unit of energy, is 3. So we have 3 states of system B that can combine with the state HT to form a state of the total system. So these are the states of the total system formed by combinations of the state HT of system A with these 3 states of system B. And if we ask the question, how many times does state TH appear, the answer must be the same answer we obtained for the state HT because they have the same energy, so we have the same complementary energy. So also 1, so here we have also 1, so GB of 1 is 3. And if we ask about the state TT, it appears 1 time because we have only one state of system B having the complementary energy. The complementary energy now is 0 because the energy of the state TT is 2, so 2 minus 2 is 0, and GB of 0 is 1, so GB of 0 is 1. Now, in this lecture, we're going to consider again a system A interacting with a system B, so in thermal contact with system B. We're going to consider that the total system is macroscopic, but system A could be small. It does not necessarily need to be macroscopic, but system B has to be macroscopic. And we're going to apply this logic that we have just reviewed to answer the question, what is the probability that system A is in a specific state beta? So we're going to suppose that there is a state that we're going to call beta of system A, and we want to know what is the probability that if the two systems are in equilibrium, we're going to find the total system in a state in which system A is in a state beta. So as we've just seen, the number of times a state of system A appears in the list of states of the total system depends on how many states of system B can combine with the state of system A. So if we're looking at state beta, then we have to consider the number of states of system B having the complementary energy. So here, this is the symbol for the energy of state beta, and this is again the total energy. So this is the number of times that the state beta will appear in the list of states of the total system. Now, if this is the number of times the state beta will appear in the list of states of the total system, and if the number of states of the total system is n, then the probability that we're going to find the total system in a state in which system A is in the state beta is given by the number of states of the total system in which system A is in the state beta divided by the total number of states of the total system. So, for example, if we consider again a system where system A has 2 coins, system B has 3 coins, and the total energy is 2. So in this example, beta would be either the state HH or the state HT or the state TH or the state TT. The number of states of the total system in this case is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we ask, what is the probability of finding the state HH in this list? The answer is 3. So 3 out of 10 states will have system A in the state HH. So the answer is 3 out of 10. So GB of U naught minus the energy of the state HH is 3. If we ask what is the probability of finding system A in the state HT, the answer is again 3 out of 10, because the state HT appears in 3 of the states of the total system. If we ask what is the probability of finding the state TH, the answer is again 3 out of 10, and the probability of finding the state TT is 1 out of 10. Okay, so let's consider again a general case where system B is macroscopic. So this expression is not very useful, because if the total system is macroscopic, then we cannot calculate this number. We cannot find the number of states of the total system. It will be practically impossible. So what we can do is to obtain the relative probability. So we divide the probability of finding system A in a state B by the probability of finding system A in a given state alpha. Since we have the same number of states here, the number of states disappears. So we end up with this ratio. And now we recall our definition. So we have defined the entropy as being the product of Boltzmann's constant and the log of the multiplicity, and the temperature, the inverse of the temperature, as being the derivative of the entropy with respect to the energy. So we can re-express this ratio in terms of the entropy. So since the entropy is Kb times the log of G will be S over Kb, which means that G is the exponential of S over Kb. So since G is a function of the energy, the entropy is also a function of the energy. So now we're going to require that system B be much, much bigger than system A. So if system A is not macroscopic and system B is macroscopic, then it clearly is the case that system B will be much, much bigger than system A. But system A could also be macroscopic. So in this case, we need to denote explicitly that we are requiring that system B be much, much bigger than system A, even if system A is also macroscopic. So to do that, we're going to change the letter from B to R to denote that system B is a reservoir, which is the technical term for a very, very big system. So we're going to repeat the same analysis, but now using the index R to remind ourselves that we are assuming that system B is a reservoir. Now, if system R is much, much bigger than system A, then it follows that the total energy must be much, much higher than a typical energy of system A. So this physical fact motivates the expansion of the entropy around the total energy, because now this term, which is the energy of system A, will be very small compared to this term. So this is the Taylor expansion around the total energy. And if you have not seen Taylor expansions yet, don't worry, just accept that this approximation is valid. And notice that this term, the second order term, this term involves derivatives, second derivatives of the entropy with respect to the energy. Since the first derivative is related to the temperature, this term here, the second order term, involves derivatives of the temperature of the reservoir, because this is the entropy of the reservoir. So the physical meaning of the second term is that it captures variations of the temperature of the reservoir when the reservoir is put in contact with system A. So for example, if system A is our semiconductor, system R would be the lab. So this term depends on how much the temperature of the lab changes when we bring the semiconductor inside the lab. So this is a term that we can neglect because the reservoir is much, much bigger than our system A. The semiconductor is small, the lab is huge. So this term here can be neglected. And you can also understand that it can be neglected just because epsilon will be small compared to U naught. So we are changing the entropy only a little bit around the central value. But in both from the mathematical or physical point of view, the conclusion is that this term here can be neglected. So we keep now only the first order term of the Taylor expansion, and we identify this term with the inverse of the temperature. So notice that we can only neglect the higher order terms if the reservoir is indeed much, much bigger than system A. So if system A is another lab, you open the door of your lab and system A is another lab, then we cannot assume this because the temperature of one room will affect the temperature of the other. The condition here is more similar to we bringing the semiconductor into a new environment. Okay, so using the Taylor expansion retaining only the first order term, this term is reduced to this, and this term is reduced to this. So now we move this exponential to the numerator, then it picks up this negative sign. These two terms cancel each other. We end up with these two terms, then we move this part back to the denominator. We end up with this expression giving the ratio of the probability of finding system A in the state beta to the probability of finding system A in the state alpha. So notice how amazing this result is. We have not specified anything about system A and anything about the reservoir apart from the fact that the reservoir is much, much bigger than system A. So without specifying any detail of system A, we found an expression for the probabilities that depends only on the energy of system A and the temperature of the reservoir. So this is a truly amazing result, and it is one of the major results of statistical physics. Okay, so now we need to use our result to obtain the absolute probability. So to do that, we remember that if we add up the probabilities of all states of system A, we must obtain 1 because system A will be in one of its states. So suppose that system A has m possible states. C1 is one state, C2 is another until Cn. So if we add up all these probabilities, we must obtain 1. And now we divide both sides by the probability of one of its states. I chose C1 as an example. And we can now use the relative probability. So this will be this exponential, and this is the energy of state C1, this is the energy of state C1, this is the energy of state C2, this is the energy of state C1. So we are using our result to express the relative probability. So we get this expression. So since we get the same denominator in all of these terms, we can group them into the numerator like this. So we have a probability of finding system A in the state C1. It's given by this expression, and notice that the sum involves the energies of all states of system A. So here we can express this same result in a more elegant way using the symbol for sum. The sum must run over all states of system A, so from 1 to m. And of course, we could repeat this exercise to obtain the probability of any state of system A. So the probability of a general state Cn is given by this expression. The only difference is that the energy here now is the energy of the state Cn, but the denominator is exactly the same. So this term in the denominator, this term is called the partition function. So we call this sum the partition function, and we call it a function because it depends on the temperature. So the partition function is a function of the temperature. So notice that this is a sum carried over all states of system A. So using the definition of partition function, we obtain this expression for the probability of finding system A in a state Cn when system A is in thermal equilibrium with a reservoir at temperature T. So that's it. This is the main result we wanted to derive in this lecture. We're going to use this result in the next lecture to find the average energy of an ideal gas. It is a major result of statistical physics, as I have already repeated often. So just to conclude this lecture, let's calculate the partition function for an example where system A again has two coins. Notice that we cannot consider system R, the reservoir, as having only 3 coins like we considered before. Now the reservoir is a macroscopic system, so it must have molds of coins. But system A can be either macroscopic or microscopic, and here it is an example where it is microscopic. So in this case, we have 4 states, so the partition function will involve 4 terms. These are the energies of each one of these states. So the energy of the state HH is 0, so we get 0 here. The energy of this state HT is 1. The energy of the state TH is also 1. And the energy of the state TT is 2. So we just need to evaluate this sum to get the partition function and use this expression to find the probability of finding system A in any one of these states. So Cn here would be either HH or HT or TH or TT. Okay, so with that we conclude this lecture, and in the next time we're going to use the partition function to calculate the average energy of an ideal gas. So I see you next time.